part of the do now today was being able to convert from one unit of measure to another. And if we go back to the do now section, you'll see that we're asked to take 2.75 atmospheres, change it to pascals, and then change that into torrs. And so we'll just do a little video here on how that's going to work. And you're going to see it happen right here. I'll give you an example. It's not the same thing as the do now, but it's going to be work the same. And this is the model of how I would like you to do this particular problem. So you're going to be given atmospheres. And let's make it 8.5. It'll be a slightly different number. 8.5 atmospheres. I want to keep it simple so we can see what's happening and not get lost in the numbers. So if I have, I shouldn't say atom, okay, atmosphere. All right, let's try one more time. Atmospheres, ATMs. Okay, that's my given now, and I want to change that to something else. So that's the given over 1. Now I'm going to need an equality, right? I want to change this one. I'm going to define this problem right now. We're going to go atmospheres to kilopascals. All right, that's the equality, because 1 atmosphere is equal to 101.3 kilopascals. So let's write the equality before we do anything else. 1 ATM is equal to 101.3 kPAs. Okay, so now that I have my equation, all I have to do is, or my equality, I should say, all I have to do is make that into a fraction, right? So I'm going to take my ATMs. Does this look familiar? ATMs on the bottom. What side of the equation is ATMs on? Left side. And what's the number with ATM on the left side? 1. That's how you know. Now this guy is a multiply, isn't it? So I have 101.3 kilopascals, and we're going to get a number here. Okay, so we ran the calculation. Now we have converted atmospheres into kilopascals, and I put a box around our answer. And by the way, we should also, oops, we didn't want to do that. Let's see if I can make that not happen. There we go. We also want to cross these guys out so that we can see clearly that we have a kilopascal as our final answer. Now, I'm asking you to do this in order. So I'm going to take my kilopascal number, and let's do this in a different color. The 861.1 kPAs, kPAs over 1 is going to be my next conversion. And let's look up at the top now, and let's circle the ones that make this particular calculation. And if you're wondering where you find the numbers across the top here, we have a handout today, and on that handout, on the back side, you're looking at the very bottom of that page. That's what I took a picture of. Just the bottom of the page. Everybody see it? Okay. Now, this time, I'm going to circle something different, because we're starting with kPAs now, and I'm going to define the problem. I want to convert from kPAs to pounds per square inch, PSI. Okay? So, again, I'm going to need an equality. So, 101 kPAs, 0.3 kPAs is equal to 14.7 PSI. What? Oh, thank you. The A in kilopascal. Yeah, I keep doing that. So that doesn't look too good, but I got it in there. Now, let's look at how that's going to affect our calculation. And let's also get this guy separated so it doesn't, well, it's at least a little less confusing. And as we go down here, we're going to have to put in the kPAs on the bottom, right? What's the number that goes with kPA? 101.3 on your radio dial. And what goes on the top? 14.7 psi. 14.7 psi. And let's run the numbers on that. Okay, there's our number when we run the calculator, multiplying 861.1 kilopascals by 14.7. We only have 3 sig figs, which is why I rounded it to what I did. And we have 3 sig figs because of this number right here, which is only 3 sig figs. So the unit of measure now is PSIs, and I've done my second conversion. And these two guys, of course, are going to cancel out, leaving us with the PSI, which is what's in our final unit of measure here. And that's how you do those kinds of conversions. We realized that we had done the number wrong, and basically the problem with the first number was we had forgotten to do the division using this number, and that, of course, made the answer quite smaller. So it's actually 125 PSIs, and that's our final answer doing the particular calculation. Okay, the next thing we did before we turned things in was to look at our lab results. And what I wanted to do was calculate the percent error in our actual versus theoretical. And if you look at this diagram, I put this up on the board during the lab, and I wanted you to copy that down. I have added these two things here, okay, actual and theoretical, because the left side over here, which was question number 7 on your lab, would you all look at that right now? You're going to be turning this in just a moment. Number 7 on your lab wanted you to get the rates of chlorine, which is right here, chlorine versus hydrogen, and then we wanted the rates of methane versus nitrogen. Now these are your actual counts, and so you plugged in your counts and you came up with a decimal answer, which is what this is all about, and that decimal answer and that decimal answer constituted your answers for question number 7. What I want you to do right now is open up to your whiteboard section and copy this in as part of your do now. You want to copy the whole screen. Okay? I needed you to copy not only the whole screen, but instead of writing in answer as decimal in the red boxes on the far right and the far left, I want your actual answers. Okay? Because you're going to use those to do a percent accuracy, or percent of error, actually, percent of error that we're going to look at as part of the do now. Okay, has everybody got that now? Actual represents your counts on the computer. Theoretical is the calculation that you did on the molar masses, which you had the upside down, the inverse of the rates for the molar masses, and the molar masses being inverse to the rate insofar as the substance, not necessarily the value, or definitely not the value, because when I take the theoretical numbers that I'm calculating on the right side of this, does everybody know where this came from? What's the name of this? What is it? What? Yes. Okay. Graham's law of effusion. So the Graham's law of effusion had the rates on the left-hand side, and it had the molar masses, which states that the rates are inversely proportional to the masses of the two molecules that you're comparing the rates of. And the way we got the rates was by counting how many hits there were on the side of the container, right? Okay. So that's what we're calling in this particular calculation our actual. Questions have come up And where are you going to copy this? It needs to be in your whiteboard because you're turning in your lab. I want to do the calculations as part of the do now. Okay? If your counts in your lab were 100% accurate and the computer program that does that were 100% correct, these two numbers would come out the same, but they never do. Which means there's two problems. One is getting the counts right, and that's not really a experimental error, but we're going to count it that way today. And the other calculation is 100% accurate, but your computer program is not going to give you accurate numbers. It's not going to be 100% accurate. So we're going to see that in a difference. Okay. Okay, I changed the top of this screen to read copy everything to do now in bigger form because for some reason we weren't getting it the first time around. Okay, so now we're going to percent error or the relative rate of for the relative rate of effusion or of the relative rate of effusion of chlorine to hydrogen, and then we're doing the other one, which is from methane to nitrogen. Now, you did this before in the lab, and we've used it once or twice since, but I thought since it's been so long, we needed to see this again. The theoretical is what you calculated in that Dalton, not Dalton, but come on. Graham's, yeah, Graham's law of effusion. Thank you. In Graham's law of effusion. So the theoretical is that number that's in the square root sign, okay? And you take the square root, you get a number that will represent the rates. And so the calculated was the right-hand side of this screen, okay, the molar masses side, and the actual is your left-hand side where you did your counts. And so when you do this, this is an absolute value. That's what these lines mean on each side. So if you subtract the two and you get a negative, don't worry about it. Just change it to a plus. And then theoretical minus the actual divided by the theoretical. Times 100 is going to give you your percent. What I'm expecting you to do for the do now is to give me two numbers when I call on you. One is going to be for the calculated and one for the actual. Okay, we're going to see what is that difference going to be. And the difference is what we call the percent error. So again, Theo is the right side. Your counts are the left side. Okay? And you're going to do that calculation twice. Once is for this guy here, and the second one is for this guy here. So you need to copy that equation down so you can make those calculations. And you can abbreviate theoretical as Theo. I always do. Theo minus actual is divided by Theo. So the difference between Theo and actual is what we're trying to figure out, and is that a significant number? So if you're less than 50% error, you've probably done things pretty correctly. If you're up around a 90% error, then you probably did something wrong. It shouldn't be that far off. Okay. Okay, once we showed all this stuff, we had everybody turn in their homework paper and their lab paper, and then we went on from there.